So we've talked a little bit about the periodic table and effective nuclear charge. Now what we want to do is use our periodic table to help us predict certain trends in the periodic table. We call these periodic trends. And the first periodic trend we're going to talk about is atomic radius. Now, a periodic trend is some property, some measurable property, that has a definite trend as you move through the periodic table. And when I say move through the periodic table, I mean as we're going, as we're sort of looking in a particular column, so as I'm going like left to right on a periodic table or up and down on the periodic table, some sort of general trend depending as I'm looking at the periodic table. That's what I mean by periodic trend. And so the first periodic trend we're going to talk about is that of atomic radius. So atomic radii is defined by the average distance of the outermost electrons. So the distance from the nucleus to those outermost electrons. So let's consider for a moment two atoms, hydrogen and helium. The outermost electrons in those two atoms are in the 1s orbital. The 1s orbital. So in hydrogen, there is one proton in the nucleus, and there's one electron in that 1s orbital. In the helium, however, there are two protons and two electrons in the same 1s orbital. So the question is which one of these is smaller? Well, remember the two things that help dictate effective nuclear charge. We talked about distance from the nucleus and the number of shielding electrons. Well, if I can somehow double the attractiveness of Carrie-Anne Moss, that would make everything different. That would make me even more attracted to her. So in this case, I have helium. It has two protons as opposed to only one proton in hydrogen. And so that nucleus for those electrons in helium are extra special. The nucleus is much more attractive. And the two electrons in the 1s orbital, they're in the same orbital, and so they're not shielding each other. So the electrons in helium are much more attracted to the nucleus than is the one electron in hydrogen, because the nucleus is twice as positive, twice as attractive. So in this case, helium is actually a smaller atom. We'll find out that helium is the smallest neutral atom on the periodic table. So as I go from left to right on the periodic table, I'm always putting electrons in the same orbital, the same value of n. I'm putting electrons in the same orbital as I go from left to right on the periodic table. But I'm not adding any more protons. Or I'm not putting in a higher energy level. All orbitals, every single orbital in an atom gets smaller as we add protons. Right? So hydrogen has a 1s orbital. Hydrogen also has a 2p orbital. It also has a 3d orbital. Hydrogen has all of those orbitals. In the ground state, there are no electrons there, but the orbitals exist. Those mathematical models and those mathematical probabilities still exist, even though there might not be an electron in it. As you add protons, every one of those orbitals gets smaller. Right? So the 2s orbital in helium is smaller than the 2s orbital in hydrogen. Even though neither one of those atoms have an electron in a 2s, in helium it's smaller than in hydrogen, because all of the orbitals get smaller, because as I add protons, the nucleus gets more attractive to the electrons, and so the electrons are sort of pulled in by that attraction in the nucleus. What about boron and fluorine? Boron and fluorine. So here's boron, ends in a 2s1, and fluorine ends in a 2p5. So we're both putting electrons in the same orbital, the 2p orbital. So there's no difference in shielding electrons, because the shielding electrons are, the 4 electrons that we put in, in the 1s and the 2s. So the total number of shielding electrons is the same. But what is different between boron and fluorine is the number of protons. In the case of boron, we have 5 protons and 1 electron in that 2p orbital, whereas in fluorine we have 9 protons and 5 electrons in the 2p. Now the electrons in the same orbital do not shield each other that much, and so because the fluorine has 9 protons, all of those electrons, including the valence electrons, which again, we're talking about atomic radius, so we're only concerned about the valence electrons, those valence electrons in the fluorine are more attracted to the 9 protons in its nucleus. So in this case, fluorine is the smaller of the two atoms. So that's sort of our periodic trend as I go from left to right. As I'm going across a particular row, I'm adding more protons into the same shell, and so the atom gets smaller because all orbitals get smaller as you add protons. Recall, meaning we've already talked about it, that the quantum number n, the principal quantum number, is a function of orbital size. It's proportional to orbital size. So let us consider sodium and potassium. The outermost electron in sodium is in a 3s orbital, and the outermost electron in potassium is in a 4s orbital. So which one of those orbitals is bigger all the time? Well, the 4s orbital in potassium is always bigger than the 3s orbital, because 4 is bigger than 3. So we now have sort of our total periodic trend that as we go from left to right and top to bottom, actually the atomic radius becomes bigger as you go sort of down and left on the periodic table. Down and left on the periodic table gets bigger, or you could alternately say it gets smaller as you go up and to the right. So the smallest element on the periodic table is actually helium, and the largest element on the periodic table is francium. So as I go from left to right, it gets smaller. As I go from top to bottom, it gets bigger. And here's sort of, a picture of all the A compounds for the first 4 rows on the periodic table. And these are all relative size, right? So these are all to scale. So as you can see, helium is the smallest atom up here in the upper right-hand corner, and francium is the largest. And what I also want you to notice is that as you step from left to right, as we go across a column, the changes in atomic radius are bigger, are not as big as when you take a step down, right? So as you can see, between group 3A and group 7A in the same column, the sizes are almost identical. But as I go from this row to this row, there's a big jump in size. Same thing, you can sort of see it even better if you look at the alkali metals, in that when we go from sodium here down to francium, it gets much, much bigger. So that's the periodic trend sort of for atomic radius. Now, we can use the concept of effective nuclear charge a little bit. The other electrons in the system are a little bit, do have an effect. Not so much when the neutral atom. But what happens if we start adding electrons or removing electrons from a neutral atom? What happens then? Well, let us consider the concept of parents and kids. So, a woman goes to the park with her one child. And if it's just her by herself with her one child, she can keep a pretty close eye on that kid. Won't get very far because she's always watching him, right? So far, so good. But what happens if she's not there with one kid, she's actually there with 8 or 9 kids that she's responsible for? How tight is she going to be able to sort of hold on to all of those kids? Well, the answer is not very tight. Why? Because she has to sort of spread out her energy in terms of kid hanging on to. She has to spread it out amongst many, many children, because there's only one of her. So they're going to get a little bit farther away. What happens, though, if we, add a few more adults? Maybe a couple. As we add more adults, if we keep the same number of kids, the more adults we have, the tighter we can sort of draw them all back in, keep them closer, we have more people to take care of them, things like that. Right? So, the kids how close the kids are a function of not only the number of kids, the total number of kids in the system, but also the number of adults. So let us compare which kids are being held. I compare one adult and one kid, how tight those electrons are, those kids are being held to, as compared to when I have one adult and 3 kids. Well, if I got 3 kids, they're going to be held a little bit looser, the kids are going to get a little bit farther out. Alternatively, if I have one adult and 3 kids, if I add 2 adults, those 3 kids are going to be held a little bit closer. So, let's talk brass tacks. Let's compare the atomic radius of oxygen, a peroxide ion, O minus 1, and an oxide ion, oxygen minus 2. How are they the same? How are they different? In all 3 cases, I have 8 protons. Right? So, in our analogy, the number of protons is the number of adults in my system. and the kids represent the electrons running around rampant. So in all three cases, it's an oxygen atom, so I have the same number of protons. But in a neutral oxygen atom, I have 8 electrons. In a peroxide, I have 9, and in an oxide, I have 10. So in the oxide, I have two more kids that I have to hang on to. So I still have the same number of parents, I have the same number of protons, but I have more electrons that I need to keep track of. And because there are more electrons, each of the electrons is not being held onto as tight, gets a little bit bigger. So in this case, oxygen, the neutral oxygen atom is the smallest, and the oxide ion, with 10 electrons to its 8 protons, is the largest. So that's if I have one element, one atom, different ions. What about these three species? An oxide ion, a fluoride ion, and a neon ion, or a neon atom. How are they the same? How are they different? Well, in this case, all three of them have, they have a different number of protons. So oxygen has 8, fluorine has 9, neon has 10. But what they do have the same number of is electrons. In all three of those species, there are 10 electrons. So in this case, the number of kids is the same, but the number of parents is different. So, knowing that neon has more parents than oxygen, and they're, keeping track of the same number of kids, who's keeping track of their kids more, tighter, if you will? That would be the neon. So in this case, the neon is the smaller of the atoms, or the smaller of these three species. And again, to give you sort of a scale model, here are the relative sizes of a bunch of elements and their individual ions. So as you can see, the difference between lithium and a lithium plus 1 ion is almost a factor of 3. Sodium, not so much. In beryllium, notice that beryllium has lost 2 electrons. Its common oxidation state is plus 2. And again, its size changes dramatically when you remove those 2 valence electrons. And on the far side, you can see, in the group A metals, sodium and magnesium, that the positive ion is smaller than the neutral atom. But on the other side of the periodic table, here's fluorine. Here's a neutral fluorine atom. When it gains an electron, so I increase the number of kids, its atomic radius almost doubles. Same with chlorine and same with bromine. And also with oxygen. So as I add electrons, if I keep the same number of protons, as I add electrons, the relative size, or the size of that particular atom,